Hi, I'm Catherine Scott. I'm the developer advocate for an organization called Open Robotics, and I'm here today to talk about ROS2 Foxy for production robotic systems. So, quick overview. We're going to talk about ROS2 in four parts. First, I'm going to give you guys a bit of social proof about the size and shape and scope of the ROS community, and hopefully this will motivate you to pay attention. And then I'm going to talk a little bit about the history and philosophy of ROS. I think the history sort of drives the philosophy, and then the philosophy drives how things are constructed. And if you know the history, you kind of understand why ROS looks the way it does. Then I'm going to talk about what's in the box, sort of what the components are, what they do, try to make the notion of ROS a little bit more concrete. And then finally, I'm going to talk about the community and the resources that are going to be at your disposal when you're building a robot with ROS. So why should I care about ROS2? ROS2, or stands for Robot Operating System 2. And it's not quite an operating system. It's more of like a layer on top of Linux operating system to build robots. As far as I know, it is probably the largest, oldest, and fastest growing robotics ecosystem for robotics. And it's also free and open source. So why don't we start with a little bit of social proof. ROS2 was basically built and directed using a technical steering committee plus community feedback. And so the slide kind of gives you an idea of who's on the ROS technical steering committee. And by looking at the companies there, I think you get a pretty good sense of the size and scope of the project itself and who's working on it, and perhaps why they think it's important. If numbers are more of your thing, I have a bunch of stats on the size and scope of the community. I personally maintain a list of companies that are using ROS. It's well over 300 companies. There are Fortune 50 companies. There are small startups, and then there's all the size and shapes of companies and nonprofits in between. In 2019, we had 264 million dev downloads. As I'll talk about later, we have a Q&A user forum that's got 35,000 users. We also have just a discussion forum that's got about 5,000 active users. Last time I searched GitHub, it was well over 2,000 repositories of ROS packages. We have a wiki, which hosts a lot of the ROS documentation. We get close to 200,000 wiki visits a month. And we're just wrapping up conference season here. As of right now, the original sort of ROS paper has over 7,000 citations. So you can see it's being used a lot in research and development. On the right is just a graph. We actually keep a metrics website called metrics.ros.org where you can actually go and look at some of these numbers and see how the community has been growing and sort of how different ROS distributions are being used. I just want to drop in there. I said Linux, but recently Microsoft has released a lot of tooling for ROS, and it is possible to get ROS2 running on Windows. And the thing that I think is important about this is that for the kind of commercial applications that I think a lot of people want to build, this is actually quite helpful. All right, so why don't we talk a little bit about history? And ROS has a long history, even though you may have never heard of it before. So let's start at the before times. And when I say before times, I mean the late 90s, early 2000s, a long, long, long time ago. The nature of robotics is much different than it is today. I just grabbed a quick screen cap of like a business article that sort of takes a look at robotics from the 80s and 90s. And back then it was a very capital intensive domain, right? So it was very, very large companies building, very, very precise assembly lines, and very few people sort of had robotic technology. Most of these systems were sort of bespoke, put together by system integrators. So these people that kind of come out and build the system for you, they were proprietary. They had very specialized hardware controllers, very vendor driven, very feed forward, meaning that there weren't a lot of sensors. It just sort of did what it did, and very sort of Windows centric. So right when I sort of left undergrad, things started changing. And I think sort of the moment in my mind when things really started taking off is about in 2004 with the DARPA Grand Challenge. And what this event was, if you're not familiar, is America's Defense Advanced Research Project Agency said, let's sponsor a $1 million competition where organizations go out into the desert and they take a vehicle and they see how fast and how far along a track, basically a race, they can get an autonomous vehicle to go. This is 16 years ago. And so I think that was the moment when people started realizing, oh, well, maybe robots aren't just limited to the shop floors and very specific tasks. Maybe they can actually do more complex things. So approximately at that same time, you see things like, Google had an IPO. You start seeing the rise of technology companies, particularly in Silicon Valley. And all of these things in the early 2000s, this idea of flexible robotics, IPO money, and sort of, for lack of a better word, Web 2.0 companies that are built on free and open source software, all sort of are swimming around in this pot. And out of this pot comes an organization called Willow Garage in 2007. And the whole idea behind it was, let's go and build some free and open source software for building these kinds of robot applications. So from Willow, this organization that was sort of funded from this IPO money, we got 3 big open source libraries that you may or may not be familiar with. One is OpenCV. So OpenCV is Open Computer Vision. So it's the library powering a lot of these computer vision applications that you see today. Another one of them was ROS, which we've talked about a little bit. And then the other one was PCL. So you have these 3 open source projects floating around. And then Willow also built 2 robots that were really geared at, one was geared at research, which is the PR2, which is that robot on the right with the arms and the mobile base. It's probably one of the most sophisticated robots on the market at the time. And the second one is a robot that's still around today in a different incarnation, and that's called the Turtlebot. And the Turtlebot was really geared at this, let's make this, affordable robot that graduate students and engineers and the people who are going to build these robotic technologies in the future can get their hands on and start to learn. So not only did they build these things, but since it was open source and since it sort of had a research focus, these technologies started to span the globe. People, Willow sent out these robots, with the Turtlebot and the PR2, to all these different research organizations. People would build their applications on top of, starting from ROS instead of starting from scratch, and then, send back their contributions or their small changes or their feedback on what was going on. And so this sort of shape and structure of a federated research community sort of indicated how ROS was constructed, in the sense that, well, it's not just one monolithic library, it's really a set of tools that allow for, distributed collaboration across the globe. So unfortunately, in 2013, Willow folded, but the sort of organizational structure, all of that open source had a soft landing, in the sense that different organizations rose up to sort of take on the mantle of the project and continue contributing to it. So my organization, Open Robotics, is sort of the steward of the ROS library. We have a partner organization called ROS Industrial that focuses on taking ROS and delivering it to the industrial community. So why don't we talk a little bit about the philosophy of ROS? This philosophy sort of comes from the history that I gave earlier. And I think the big thing that came out of having this global research community is the notion of federation over centralization or decentralization. And that's something that I think has fallen out of favor recently, but it's really important, especially now. And the reason that it's important is that this federating or decentralizing allows different people to do what they do best and contribute it back to the whole. And so when you look at things like the ROS build systems, people sometimes wonder why you have this fairly complex build system. And it exists such that you can take different packages and different languages from different places and put them all together into something that still works. Philosophically, I think ROS generally aims for small, simple, composable utilities that can be shared. This is very much like most Unix command line utilities. They're small, and then you take these individual parts and you agglomerate them together to do more complex things. Again, I think there's a philosophy of not reinventing the wheel. If there's something already existing ROS, go and use that. If there's a message type for a particular sensor class, go and use that, because the more sensors that we have, that are working with the de facto standard, the more things that can be built on top of it. The next two are a little strange, but I like to say it's non-exclusive and inclusive. So one misbelief that people have about ROS is that you either use ROS or you use something else. And that's not always the case. You can actually, if you have something, one component that isn't a ROS component that you think is actually better, some sort of real-time component or some sort of control system, it doesn't mean, you can't use ROS. You can, use that component and bring in all of these ROS tools on top of it. And that's really, I think, quite powerful, but people kind of miss it, is that you have this cool thing, and you can bring all these other cool things into play. And then finally, I think with all open source, it's about freedom and being able to not be locked into vendors, to go do what you want and to build the things that need to be built. So as I said, ROS sort of started in this 2007, 8, 9. We've been going nonstop since then. So the final ROS version, or ROS 1 version, ROS Noetic, was released in May. So that's the last version of ROS 1. ROS releases are given sort of sequential names. So the first one was A, and then there was B, so box turtle, sea turtle. They have basically a different lettered name for each release over the years. So that all continued up until the present day, but somewhere around approximately 2017, after about a decade of developing the system, people said, wow, this is great, but we've learned a lot. We understand now what it'll take to move this software sort of from the R&D domain into the production domain. And the decision was made, well, let's make a new version. Let's keep all the best parts. Let's change some of the network infrastructure to make it more secure. Generally improve security by shrinking those network surfaces, improve robustness overall, and then just sort of fix the things that need to be fixed. And we'll make a new release, ROS 2, and we'll bring that to industry. And so ROS 2 was born. We're now on the 6th ROS release, so it's ROS Foxy Fitzroy. And this is the sort of release where we're saying, we redeveloped this thing, we've gone through multiple iterations, people have used it in the field, and we're finally comfortable asking people to say, hey, give it a try for these mission critical applications. So I talked a little bit about the history and the philosophy, but you may still be asking, well, what's inside of this thing? How does it work? What are the components of ROS? What do they look like? And I'm going to give a few very high-level examples of kind of what's going on, so you can kind of understand what the components are and where you use ROS. So as I said before, the sort of philosophical thing is don't reinvent the wheel. So let's talk about some of the wheels that are there in ROS. And just to motivate this with examples, to talk about things at a high level, I like to say that traditionally robots have 3 key components. And those 3 components are sensors, which take in data, actuators, which are wheels or a linkage in an arm or some other component like that. And then finally, there's control. And control takes in all that data, does something with it, and then moves the actuators. So these are 3 parts. Let's talk about how they're connected and what they do. So the first thing we should talk about with ROS is sort of multi-process control. And in ROS, we call these nodes. And a node is basically a process encapsulation that can come in a variety of different programming languages. ROS has a bunch of tools to compile these nodes, install them, start them, stop them, pause them, query their status, and do all your command line argument parsing. And basically what ROS lets you do is build a limited number of processes in a bunch of different languages across a bunch of different packages. And when I say packages, a package is that sort of small, discrete process of or collection of processes that are all sort of logically grouped. So in this example, we haven't really done anything, but if you imagine sort of the bubble that says sensor, the bubble that says over the hands, that it says actuators, and the bubble over control, imagine each of those are packages, and then inside of each package there might be a node that is the process that is running. So ROS allows you to basically take nodes and launch all of them at the same time with a little bit of logic. The nodes themselves can be constructed out of C++, out of Python. I've seen people build stuff in Java and JavaScript. There may be hardware in the loop. There may be some configuration parameters on the start of each of these things based on your hardware configuration, which lends itself to having some control flow. And if you imagine if you had a large complex robot, like say an autonomous vehicle, right, where there's all these different pieces of hardware, all of these different processes running, processing the data, all of these other small processes controlling, the speed of the vehicle or the wheels on the vehicle. How would you go and write a shell script to bring those all up concurrently? And if you say that to somebody who's been working Linux, like, oh, geez, that'd be really, really hard. It's not something that sounds fun. It sounds prone to error. There'd be a ton of these shell scripts around everywhere. And basically ROS handles that all for you. So that's the first thing you don't really have to reinvent or think too hard about. The next thing you shouldn't reinvent is the notion of topics. So ROS nodes communicate over topics. So in our example on the right, there's basically a sensor which is an eye. It probably has an images topic, right? It produces images 30 times a second. And those images go to your brain, and then your brain does something with them. And it will send out a message at some point to move your hands around at some position, left hand, right hand. So ROS topics are basically a cross-language serialization primitive, like Rabbit or like protobuf or like something you'd see in RabbitMQ, but it's just a tool to basically move messages between each of these processes in a standardized way. So ROS also, in sort of its build system, has standard messages that most people use for most applications. So that's to say image messages or trajectory messages or transform messages. But generally, there's a whole library of standardized robotic data primitives that are already built into ROS. There's also a ton of tooling for introspection and working with these topics and moving data. And finally, there's a lot of utilities for namespacing data, so you can keep it all logically together and sort of understand the layout of all of the signals moving around your robot. So just to give you an idea of what this looks like in practice, right? Imagine we replace our eye now with a camera, and what the ROS messages will allow, since the brain always speaks in these image messages, you can just pick that eye up, wire in the camera, and hopefully, since it speaks the same message, that just is plug and play and it works. Maybe a little bit of configuration. I think the other thing to consider about all of this is between building small discrete processes and messaging or these messaging libraries, it really lends itself to loose coupling between components, which generally speaking leads to better software. Another tool that I think is really, really important with topics is the ability to do introspection. So, I have my sensor and it's going to the brain and something goes wrong and I want to see what's going on. Well, I can actually just, using a command line utility, tap into that topic and see the images as they come through, or if it's a message, see the messages coming through. Not only that, I can see like what their frequency is, if there's jitter and the frequency of how they're being transferred, collect statistics. All of these different things. It's quite helpful. The ROS middleware, or ROS basically has a middleware system that is used to move these messages around. It's called DDS. There are various vendors and open source implementations of this DDS system. But really, by vendoring that component of ROS, you can go to that particular vendor and get them to work with you if you have particular needs. We also find that it probably will lend itself to better security overall and, in the long term, better robustness. As I said, you could kind of tap into these topics as systems are running, but I think it helps to make that more concrete and show you a few images. So one tool in ROS that people use frequently is this thing called RViz, so just ROS Visualization. RViz lets you tap in to any sort of signal, and it has all of these hooks for common data types like point clouds, like images, like LiDAR scans, and it allows you to tap in and see them. So I have a couple examples of applications that have been built with ROS on the right. This is just an indispensable tool because at the end of the day, when you're debugging or building a robot, you can just tap in, see what's going on, build sort of, for lack of a better word, a dashboard about your application that tells you what you need to do or what you need to know. And you can even go in and do a little bit of annotation and control through this interface. So you don't have to reinvent that. That's already there. So while we're talking about serialization, another sort of component of ROS that I think is important to be aware of is this notion of ROS bags. So a ROS bag is basically a standard serialization of ROS data. And you're already transferring this data, you're already doing serialization, so we just sort of added on a serialization tool to drop it to file. To make this more concrete, if you look at the example on the right, you have the sensor, the camera going to the brain. You can actually just take all of that data while the system's running and drop it into a file. And that file then can be distributed to somebody else, can be debugged, could be used for testing, could be used for machine learning, all sorts of things. I mean, the notion of bags and this standard serialization library is incredibly, incredibly powerful when you're building a robotic system. To the point where these bag files can actually be used as a drop-in replacement for your robot, which is particularly helpful, say, if you want to build robust testing in your system. So I think most people, when they're building a software system, want to have a robust set of tests. But if you think about it, with a robot, you can't actually run the robot all the time to run your full unit test suite. And so what you can do is you can actually run the system, collect a bag full of data, and then in your test, take that bag of data and replay it. And it, from the test perspective, it looks just like a robotic system. Bags are also just a phenomenal tool for a bunch of other applications. They're great for research. So you can bag a bunch of data and ship it off halfway around the globe to a collaborator. I've seen people do this with like new sensors and new sensor modalities. I think that's kind of handy. You can use it for verifying performance on a certain benchmark. You can use bags for, sort of deep learning. You catch a bunch of data, you pull out every certain frame, build your data set, and go do your deep learning. The usefulness of bags, I think, can't be understated, but don't take my word for it. So this is a data set that's all bag driven that came out from Ford, I want to say about 2-3 months ago. And it's just their entire autonomous vehicle driving data set, in adverse conditions all over the Midwest for months and months and months. You can just go and download all this data. If you're interested about learning like how to build vehicle autonomy, you don't have to go build a vehicle. You can actually get this whole encapsulated running system, take it home and start playing with it, start learning. Here's another data set that recently came out from the STARS lab in Canada, and they're working on how do we build basically autonomous rovers for planetary research. This one's interesting because it has like all the data from both like the solar cells that capture the power for the robot, as well as like battery information. So if that's something you're interested in, you can go and play with that data set, and you don't actually have to build a robot. So let's talk about another thing that you shouldn't have to reinvent, and that's services and actions. So basically, services are ROS's implementation of a synchronous behavior API. So when I say synchronous behavior API, I mean something you want to build an API for a simple behavior. The one I use most often is for autonomous vehicles. You can write a service to say, unlock the doors, wipe the windows once, beep the horn. Very simple API where it's something quick, synchronous, so it does it, it returns. But ROS already has an API for building these things very, very quickly. The other way that we like to sort of talk about behaviors is as actions. So an action is an asynchronous behavior that needs to have requests negotiated, requires preemption, which means you ask something to be started, it goes, and then you make a decision. Oh, no, I don't want you to do that. Please cancel it. So it has preemption, and then it also has status callbacks. So the example of an action that I use most of the time is, say, navigation. If you have a robot and it's sitting in front of you and you want it to go across the room, an action would sort of define that behavior, because the robot can't change its course if it's already going, so you need to negotiate request. It may run into a wall, in which case it needs to be, you might say, oh, we'll cancel that. And then you also want status callbacks. That is to say, you want it to tell you when something is happening, tell you when it's reached its goal, and so on. Most of this in C and Python can be done via a callback-based API, which I think particularly for younger engineers is very nice, because you just say, here's your behavior here, here's your behavior here, and you don't really have to think about the complicated logic of all of the async that's going on. And just overall, I think this basically allows you to build very, very robust, very, very useful behaviors fairly quickly, because everyone's working off the same sort of pattern of behavior. Another thing that's in ROS that I think is extremely important that everyone should be aware of is just general tools for handling geometry and kinematics, or as a lot of people like to call it, the hard, scary math, right? So there are tools in ROS that kind of abstract away a lot of this. You don't really have to think about it, and you don't have to reinvent it. The first thing you need to be aware of is URDIF files, which is a great Swedish sounding name, but URDIF stands for Universal Robot Description Format. And an URDIF basically defines the 3D geometry of your robot. It's basically a 3D model of your robot that'll tell you where anything is. And as you have different linkages, will actually tell you where one linkage is positioned with respect to another. And I think most CAD programs now support it, so you can just export an URDIF file from your robot, which is super handy. The other library that you need to be aware of is TF2, so Transform 2. Transform allows you to basically move coordinates from one frame to another frame. And this is an API-driven minimal mouse sort of API. So if you need to know, you have an arm or something and you're moving it around and you move out each joint and then you want to know where the finger is, TF2 will help you do that. It'll basically, you can answer this question, where's my finger given that I rotated like this or this? The graphic on the right basically shows you a quick example of that. So, given the actuators, where does the brain think it is? Well, it figures that out sort of based on what the URDIF tells it all the geometry is, and then what TF tells all the motion between all the geometry is. All right, another meta package in ROS is the MoveIt library. The MoveIt library will handle forward and inverse kinematics for you on your robot. So what does that mean? If you have, say, a multi-axis arm or some robot that has a complex kinematics, right? Where you say, I want to move the arm out to a particular position and pick something up. How do I get all of the linkages in the arm to do what they're supposed to do to get there without crashing into something? That's the problem that MoveIt solves. Inside of MoveIt, there's a bunch of different algorithms for solving that type of problem in a variety of different ways, and a bunch of tools to help you build that sort of behavior very, very robustly. Another important tool sort of in the ROS ecosystem is navigation. And so ROS has, there's multiple navigation frameworks. I'm going to talk briefly about the NavStack, which is a SLAM stack for ROS. So what do I mean? What do all those words mean? So SLAM stands for simultaneous localization and mapping, which is, hey, I need a robot to move around an environment, figure out where it is, and figure out where all the walls and obstacles are. And basically the NavStack handles solving that problem for you. And it's been used in massive warehouses. It's actually, if you go to, I want to say it's navstack.ros.org or navigation.ros.org, there is a video of a couple of robots just running multiple marathons using this nav stack. They can go for a long distance, and they're navigating busy hallways with a bunch of students running around. So it's a fairly well-tested software package that you can drop onto any robot that moves with a reasonable set of sensors. So another component of ROS that I'd like to talk about briefly that I think is extremely valuable is simulation. And you shouldn't reinvent simulation. So fundamentally, robotics ends up being hard. And it ends up being very hard as a software developer because the robot that you're working with is expensive, it's dangerous, it's generally, relative to sitting at your computer and typing compile in something coming right up, it's relatively slow. So that makes it difficult to share robots. It makes it difficult to test with hardware. It makes it just generally a very slow and tedious process to build a robot. So, most roboticists kind of say, well, why don't we not always do our software development on a robot? Why don't we do our software development in sort of a virtual machine? So ROS basically has its own capabilities to build virtual robots and then build your software and test them. And then once you're happy with that in simulation, you can go and deploy it on the actual physical robot. And so the simulation capability is called Gazebo. And the latest incarnation of it is called Ignition Gazebo. And it allows you to build multiple virtual robots and multiple large robot environments while simulating the physics of the robot and the sensors on the robot. And it plays very, very nicely with ROS2 and allows you to build, I've seen giant, basically like huge facilities modeled in Gazebo for testing robot capabilities, right? So I've seen like whole nuclear power plants that are huge, modeled in Gazebo so robots can go navigate around and see how they're moving around. I think the take home about simulation is that it allows you to build, test, and debug your robot in a very reasonable fashion. It allows developers to sort of work autonomously on their capabilities without having to be in the office, without having to be in front of a robot, which is extremely powerful. The image on the right is actually taken from a competition that was put together using Ignition Gazebo by National Institute of Science and Technology and so the competition called ARIAC is just a very, very giant simulated manufacturing floor. We have robots moving around trying to do all of these different things. And the goal of the competition was that individuals would come in and basically build all the smarts that go into this robotic system to see how well things can move and how well, how efficient they can make this factory floor. So now that I've covered sort of at a very high level the parts of ROS, like what is in robot operating system, I want to talk a little bit about the community, because the community is really where you're going to go to get help, to figure out how to put together your robot, to figure out what hardware is going to work well with your system, to figure out what tools are already available. And so there's a lot to cover because it's a large sort of international community full of people working on projects. So the first thing to sort of talk about is the notion of ROS packages, which I like to say is sort of batteries included, stealing from Python. So ROS has this concept of a package, which is roughly a collection of code, ROS nodes and ROS messages that can be pulled down and combined and used in your robot. These ROS packages can be C++, they can be Python, there are a variety of other languages, but primarily C++ and Python. ROS federation generally means that our build tool, ROS2 build tool, is called CodeCon. And it basically allows you to interleave these sorts of builds and build, take all of these different packages and build a system that you'd like to see in the world. The rough analogy I like to make is ROS packages are kind of like pip or Python, right? You can kind of go search for a ROS package. We actually host a bunch of binary packages on index.ros.org, and you can go take a look. And if there's something you like, something that you can use, you can go and pull down that binary, and your robot is ready to go. just in the bottom right there is one of my sort of favorite ROS packages, which is just Robot Web Tools, and it's a collection of sort of JavaScript tooling for ROS. So it's basically a JavaScript gateway from ROS, so you can build, simple web applications that interface with your robot, in a browser, which I think is super handy. Because ROS has all these packages, you can build a package around your bit of hardware, which I think gets us closer. We're not there yet, but gets us closer to sort of plug and play hardware, right? Where you can go and buy a sensor, buy an arm out in the world, and there's already a ROS interface for it. And you basically pull down the package and build it, or it may even have a binary, and you have that data, you have that actuator, and now you don't have to worry about that part of the problem, right? You're only worried about how do I wire these two things together. I just have a couple GitHub pages here from a couple packages that have been released. So like Universal Robots has an ARM driver for ROS. Both SICK and Intel, the Intel RealSense drivers also, or RealSense cameras have drivers that are just ready to go with ROS. So it should be fairly quick and easy to get started with them. While we're talking about hardware, ROS2 actually has micro ROS, which is basically a bridge between the ROS2 DDS layer and an RTOS. And currently works on NUTX. There's more in the works, but what I find really, really cool about this is that it'll eventually allow for much, much smaller robotics components that are just sort of plug and play. So if you're coming from robotics more from a hardware side, this is definitely something to go check out. So ROS isn't just code, there's a ton of community behind it. So we have sort of a giant landing page, ros.org, that should sort of direct you to all the different resources that are out there. If you're just getting started, this is a good place to sort of check out because it'll point you to, beginner resources and what you need to learn. The ROS2 documentation is fairly substantial at this point, and you'd find that at index.ros.org/doc/ROS2. Since we're concurrently supporting both ROS1 and ROS2 right now, most of the docs kind of still default to ROS1, so you need to be particular about where you're looking, but that's where all the ROS2 documentation lives. And so if you're looking to understand and start with ROS2, that's where you want to go. We also have just a community discussion forum, so discourse.ros.org. This is where you're going to go if you have a cool project that you finished, if you want to learn about new packages that are being released, and other ROS-related events. Generally, I'm there all day, so if you want to know more, let me know. But if you have particular ROS questions, we also have our own Q&A website that predates Stack Overflow, but it's just generally like ROS core maintainers and developers. So if you go to answers.ros.org, you can go and ask your questions there, and generally, somebody in ROS community will help you as best they can. So ROS2 Foxy is the 6th ROS2 release. It's the first major LTS release for ROS2, and by LTS I mean long-term support. So you'll be getting patches and bug fixes with this release for at least 3 years. Upgrading to the next release should be fairly easy, which will ROS, whatever we decide to name the H version of ROS, will have a 5-year LTS period. So if you're looking to start, now's a great time to get started with ROS2. If you're transitioning from ROS1 to ROS2, it's also a good period. It's time to start thinking about the transition. If you're just starting out, here are a couple resources that I think are probably the best resources for ROS right now that are available on the web. First and foremost, if you want to learn ROS2, the ROS2 docs, as I posted before, index.ros.org/docs/ROS2. We've been working with DARPA recently for the Sub-T Challenge. DARPA has been kind enough to help build a set of Hello World tutorials with a full simulator that walk you through the process of setting up a robot, building perception systems on that robot, using the sensors, using the nav stack. basically building a fully functioning autonomous mobile robot all in simulation. And it's a really, really good resource for those who want to learn. Also ongoing right now is an AutoWare autonomy class. So AutoWare is a sort of partner organization that works solely on vehicle autonomy. And they have I think, 12-part lecture series on ROS and particularly ROS for autonomous mobile robots, or for autonomous vehicles, I should say. You can also pick up a TurtleBot, which is our sort of flagship educational robot, and they're a lot of fun. We run ROS 2, quite fun. So thanks, and go build some cool stuff.